Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the third tutorial which is maths for AI. So the learning objectives would be focused mainly on gradient descent as well as on momentum. Now before we go into the MATLAB demo to understand and visualize, let's very briefly recap what we have read about gradient descent, learning rate and momentum. So let's assume that we have an error surface from either a single layer neuron or a multi-layer perceptron. Let's assume that theta represents all the learnable parameters, which is given as W1, W2 and so on, right. Our goal is to minimize the error, and hence our goal is to actually solve this optimization problem, which would result in theta star. Theta star is given as arg minimum of E theta for the variable theta, right. Now essentially when we look at the algorithm, our steps are, we would first randomly initialize the weights theta, and we would follow a normal distribution for now, or it could just be a random initialization. Now until the loop is converged, until we do not have a stopping criteria, until the stopping criteria is met, we will compute the gradient, which is del E by del theta. Once we have this gradient, we would update the weights. So theta is given as theta minus eta times del E by del theta. Now once this loop is converged, we would attain the best possible theta star, and this is something that would be used, right. Now if we look at it from an on the error surface perspective, let's assume that we start at this particular point. We would essentially keep running the learning algorithm until it converges, which is until it reaches this point, which would essentially mean the minimum, right. And lastly, we have also reviewed that the influence of the learning parameter. The learning parameter essentially gives us the step size for this, right. We also discussed the effects of learning parameter. Now in the weight update rule, W is given as W minus eta times del E by del W, dou E by dou W. If we plot the graph of error versus the weights W, we observe a similar phenomenon that we discussed even in the lecture, where the learning rate actually influences when and how we reach the minimum point. So let's assume that we take a very high learning rate eta, then essentially if eta is very high, which is highlighted by the red curve, we can observe that it would start oscillating. If eta is very low, then this convergence would be very slow. And lastly, we essentially want to identify the most appropriate eta, which is a moderate, which would have a moderate learning rate. So essentially a high learning rate would result in overshooting, which is something that we will observe in the demo. A low learning rate is good, but it is very slow towards convergence, and hence we want to find out the most optimal way to attain convergence. And we also went over a technique known as the momentum. This could be used to get a good or a moderate learning rate. Okay. Now let's go over the MATLAB demo to understand how the gradient descent works. Before we start, essentially gradient descent is a optimization algorithm which is commonly used to minimize the function using all the learnable parameters involved, right. The goal is to find the coefficients that result in the lowest value of the function. This is something that we denote using the arg minimum E theta optimization equation. Now gradient descent is essentially one of the very popular methods, mainly because it is used in when we are training deep learning models for various tasks, for image recognition, NLP, speech recognition, etc. So we do not need a specific algorithm while training models used for these applications. We can use only gradient descent when we are working on the learning algorithm. Right. Now there is a minor change in the notation, so please do take care. Theta is given as theta minus alpha times delta j theta, where theta are the learnable parameters, alpha is the learning rate, and delta j theta is essentially the derivative of the loss function, where j is highlighted by the loss. So essentially our E error now becomes j. Now the general learning algorithm is something we also saw in our algorithm block, where we initialize the parameters of the model using random values or using a normally initialized values. We compute the cost or the loss. We finally compute the gradients from the cost function, and as we saw in the last tutorial as well, these gradients are essential for us to give the direction towards attaining the minima value for the particular error. Lastly, we update the parameters of this model. So theta is given as theta minus eta times delta j theta, which is highlighted from the new notation as observed above. And lastly, we keep repeating these steps until we reach a converging point. Once we have attained convergence, we come out of the loop. Okay, now let's see a quick demo in the 2D space. So let's try to find the minimum of a convex function using the gradient descent algorithm. The function fun, which is fun, is given as x square plus 0.26. So in MATLAB we write it as syms x fun, which is essentially initializing these variables and then defining the functions. Once we have done that, we would essentially calculate the gradient of the function using and also define different parameters involved in the learning process. For example, n, which is the total number of intervals for the weights. We would define the learning parameters, we would define the learning iterations, which is ni, and finally we would compute the values. One more change in the notation here is v is now the weights, not w, right? Okay, so gval essentially highlights the gradient of the weights w. Now once we have initialized v, which is the starting point of w, which could be any number, essentially we try to plot this. Once we have plotted the curve, we try to use the gradient descent algorithm. Now this algorithm is the same algorithm that we saw earlier, the only difference is the change in notations. Okay, now let's take a look at how the learning rate is affected. So this is how the learning algorithm works. So we have a point initialized at v is equals to 5, and using the negative of the tangent at this curve, we try to identify the direction and move towards the minimum part. Now in this particular scenario, our learning rate is sufficiently good. Let's try to understand what would happen if I make the learning rate as very high. So let's make it as 1. If we do that, as observe, the jump is essentially from the starting point, which is v is equals to 5, to the other end, right? So this is what is happening, that the model will not be able to converge because it keeps oscillating. Now let's look at a converging learning rate which is very, very small. If we have a learning rate which is very small, we can observe that the changes in the weights is very, very gradual, right? So although it started at v is equals to 5 with a learning rate of 0.01, the movement towards the local minima is very, very gradual. And this essentially means that the learning rate should not be very small because it takes a lot of time. And again, if we have fixed the values of weights as 100, then due to the stopping criteria it may not even reach the minimum, right? And if we keep the learning rate as very high, it would just keep oscillating and not again attain the minimum value. And hence the goal should be to come up with a reasonable learning rate so that it attains the value and doesn't get influenced by the stopping criteria. Okay, now let's look at it in let's look for the same gradient descent for a different function. So let's define z as a function of xy let's define z as a function of xy, which is given as x square divided by 20 minus cos of root of 2y divided by 2 times cos of x plus y square by 2. Now if we take this function, which is apparently a very complicated function, and we try to get the gradient of this function, we get j, which is the gradient of the function z with respect to x, and then the derivative, which is dou z by dou y, which is the second element. So now we have z, which could be assumed to be the loss or the error, and we have delta j, which gives us the direction. So again, z is defined as the function here, and the gradient is of the gradient required for both the learnable parameter x and y is defined by j xy. Finally, we define a mesh grid to plot the graph for x and y. So both start from -10 to 10 in a step size of 0.1. Now again, let's look at the optimization process using the gradient descent. Again, there has been a minor change in the notation here. However, we'll just go quickly over what is the weight and what are we trying to optimize. So the learnable weights are x and y. The gradient is defined by j x and y. Hence the updated weights are x new, which is given as x minus alpha times gradient of 1, which is the first element. Y new is y minus alpha of gradient of 2, which is the second element of j, which is dou z by dou y. And finally we get this, which is the modified learn weights. Now if we just look at this particular graph on the right, we observe that the point starts in the middle, which is a randomly initialized point. However, following this algorithm, we reached a minimum point, right? And again, if we keep changing the values of alpha, which is the learning rate, you would observe similar effects that we observed in the previous curve, which is it would either become very, very slow, or else it would just start oscillating about a certain point. Okay. Now these are some things which have influences over the gradient descent, and these are some things we have already discussed, which is the learning rate. We saw the effects of learning rate, how changing the learning rate can actually influence the learning algorithm. It could either converge very quickly or it could just keep oscillating. We also saw that we can attain the local minima using the gradient descent, and this is essentially with the optimization of minimizing the error. Right. Now we will see in the next lectures about a phenomena known as overfitting. Overfitting is essentially we have a model which is much more complicated than the data required, and this is something that we would go in detail again with visualization in the next tutorial. And lastly, the values of initialization. Currently we are using a random initialization or a normal initialization with 0 mean and 7% standard deviation. However, we would see how initialization does affect the learning algorithm. Okay. Now, following gradient descent and following the influences of learning rate, we have come across a certain technique that could be used, which is defined as momentum. So let's very quickly just observe the effects of momentum in the same gradient descent algorithm. So gradient descent with momentum, We previously saw that gradient descent has been used on a similar 2D plot where we defined z and then we tried to minimize the x and y, which were the learning weights. Now let's see the effects of momentum here. Now again we will quickly go over the notations to avoid any confusion. Okay, so let's define z as the previous example, which is x square plus y square by 20. Okay, let's define z as x square plus y square by 20 minus cos of x times cos of y divided by square root of 2. So this is just a function that we have defined. Now we actually denote z, which is a variable depending upon x and y, as a loss function, right? And again this is just nomenclature, please do not get confused. We also defined j, which is then the required derivative. So j is defined as the dou z by dou x and dou z by dou y. Essentially it's a vector, right? And once we have these gradients, we'll essentially just try to plot and see the learning with momentum. Also during plotting these curves, x and y need a timestamp. So x and y axis starts from -10 to 10, right, with a step size of 0.1. Now let's also define all the gradient descent parameters. So alpha, which is the learning rate, eta, which is defined as the momentum, and max iter is the number of maximum iterations. Lastly, the convergence tolerance, which is essentially if the model has a tolerance less than this, then the algorithm should stop, right? Okay. Now finally let's also look at the momentum term, which is highlighted here. So momentum is given as gamma times Vt minus 1 plus eta times delta Wt. Vt minus 1 is essentially the momentum term. Now if we look at this algorithm, this is essentially just highlighting to us the gradient descent algorithm. We also have certain checks to see if the model has converged or not, and this could either mean checking if the change in the weights is less than the tolerance. If it is less than the tolerance, then we can stop, or actually we could also stop if it has achieved the maximum iteration. So the maximum iteration was set to be say 100. If it has crossed maximum iterations, even then we could stop. However, that would not guarantee the threshold criteria. Now let's just take a look at how this learning algorithm is working, including momentum. Now we see, compared to the earlier graph, that this actually is much faster and more stable, in the sense that it's not getting stuck anywhere, right? So it is more or less stable and attains its minima quickly. Now let's try to decrease the alpha value. So initially the alpha value was very high, and hence we saw some oscillation at the very end. However, it was not as bad. Now let's take a look at alpha, which is very, very small. If we look at this curve again, we can see that although it's pretty, although the learning rate is very small, it doesn't really affect the convergence. The convergence is more or less similar to the speed of the last example when the learning rate was very high. This is essentially because of the momentum term. Hence, in this lecture we went over some of the multivariable calculus. We saw the effects of gradient descent. This is either on a simple plot or on a proper 3D plot. We saw the effects of learning rate with various visualizations, right? We saw what would happen when the learning rate is very high. This would essentially oscillate, and we also saw how momentum can be used to address this situation. We saw that when my learning rate was very high, which is around 0.99, or if it was very low, around 0.001, it didn't really have that kind of effect because momentum was there to support it. We had seen in the lecture that momentum has an effect it doesn't let the gradient descent just crawl. It tries to push it, and then near the convergence tries to have a decent learnable rate. Hence, we saw from visualization how momentum is very helpful for the convergence part of it, for the learning algorithm using gradient descent. Thank you.